Thank you all very much for joining us. This again is our first live webinar or demo for the BioFlux instrument. Briefly today, what we're going to do is go over a platelet aggregation experiment. We're going to start by coating the BioFlux plate with collagen, different concentrations of collagen. And then we'll follow that by rinsing the BioFlux plate with BSA and PBS. We'll label blood with calcium AM, and we'll run this plate through the BioFlux protocol. The plates that we're going to be using today are the high shear 0 to 200 dyne plates. These are particularly useful for platelet aggregation experiments, as oftentimes pathological conditions go above 20 dynes. These plates will go as high as 200 dynes. Their design is a large inlet with 4 fingers that spans to a viewing area, and then a small serpentine that goes to the outlet. And that's optimized for the high shear range. In the blood clotting cascade, there are several different extracellular matrix proteins, or ECMs, that will line the blood vessels and are responsible for different processes and coagulation. The most common of these that are used to study is collagen. And so today we'll be using collagen from the Chronolog Corporation, which has been making platelet aggregometers for many years. And the particular reason for using this collagen is that it's got a full fiber length to it. And as a result of that, it allows for the platelet coagulation cascade to happen as it would in vivo. Using collagen from, for example, Invitrogen or Sigma, typically the fibers are shredded, and so the aggregation cascade does not happen at the same rate. The protocol that we'll use today is that we're going to coat 6 wells with BSA and increasing concentrations of collagen. For the purposes of this experiment, I've already done this morning, but I'll go through the steps with you, and then we will apply the blood and run it through the machine. So this is the control panel for the BioFlux plate. We will start with removing a new plate. BioFlux plates come pre-sterilized by ethylene oxide and include a sealer here that is sterilized until opened up, so that if you would like to just use a portion of the plate, you can save the remaining plate, portion of that plate for a later time. I'm going to start by adding BSA and then increasing concentrations of collagen. And I'm going to add this to the output wells. It's very important when adding liquids to the wells that you make sure that you avoid air bubbles. This usually can be accomplished just by visual inspection, looking at it. Certain liquids that are viscous may be more prone to air bubbles, so it's good to just keep an eye out for them. This is 5. The reason that we're priming from the outlet to the inlet is that we're going to load the blood into the inlet well, And we want to minimize the amount of ECM protein that is found on the inlet well if possible to avoid activating the platelet coagulation cascade before we start running it through the fluidics. So now that we've added this, apply the interface to it, and this is the 48 well interface. We're going to set the shear rate to 10 dynes. Excuse me. And the reason we're doing that is because in the high shear plates, the dynamic range of the pressure used to push the plates is reduced. For example, 10 dynes in a low shear plate would be about 4 psi, and in this case it's 0.33 psi. So this is just enough to get into the dynamic range of where the regulator is working, and to make sure that we sufficiently push the priming liquid from the outlet to the inlet without any air bubbles. And by observing from the outside, I wonder if I can, actually this camera here is picking up on this, you can see beads of liquid that have formed over here. So in this case, the plate is sufficiently primed. We don't need to completely move the liquid from one side to the other. The next step in this, we want to remove. Now, typically in a regular experiment, we would let this incubate for an hour. We're going to remove the remaining ECM from the outlet well. Very good. And we're going to apply 500 microliters of 1% PSA to the inlet well. Again, BSA has has a high protein count to it too, in addition to the collagen, meaning that any solution with large quantities of protein are more likely to have bubbles associated with them. So it's very critical to watch your wells to make sure that no bubbles have accumulated in the bottom. And back in the software, I'm going to reset it. Use 5 dynes. And we're going to apply pressure this time from the inlet to the outlet. The BSA is going to block any non-specific sites on the glass and allow for a cleaner experiment. Typically this would run between 5 to 15 minutes. After you finish that, we're going to remove the remaining BSA from the inlet. And now I'm going to add 500 microliters of PBS. The important thing for the platelet cascade to occur is to use PBS with calcium and magnesium. Most PBS comes without calcium and magnesium because it's used to rinse the cells prior to adding trypsin and EDTA. But calcium is essential for the platelet cascade, so we're going to use that. And we're going to perfuse that as well at 5 dynes. In most experiments, that goes for 15 minutes to wash out any excess BSA or collagen from the wells. Now, while that's going, we're going to take a tube of fresh blood that's been put in citrate. Citrate is the most standard and common anticoagulant for coagulation studies. Most blood is put in EDTA for the coagulation studies, not for other purposes, for isolating serum and whatnot. But in our cases, we want the blue top tube that has a certain percentage of citrate on it. And we're going to add to a final concentration 10 micromolar of calcium AM. Calcium AM will selectively bind the platelets. And of course, it's good to use the universal precautions during this. After that, we want to take in, wrap the blood with foil to make sure that we don't bleach out the system. This is a plate that I prepared this morning, which had the correct incubation times on it for the collagen coating, the washes with BSA and PBS. So I'm going to start with adding 300 microliters of PBS to the outlet well. And the reason for that is to counterbalance the blood that I will add to the inlet well. By correctly balancing the experiment, the blood should not flow through the channels until we apply pressure. When doing platelet experiments, it's always important to look at your blood before running experiments to make sure that it hasn't already coagulated. This could happen for a variety of reasons, including patient variability and how much for example, how much the donor drank the night before. After you add the blood, it's important to get started fairly quickly. A wipe here to remove the excess blood. So it goes biohazard. We're going to use the heated plate to initiate the platelet cascade. The system that we're using is a Zeiss C1 with a Mars Hauser stage, and our software is Metamorph, or Montage, which is our rebranding of Metamorph, which comprises of the 1000 system. And we're going to quickly build a stage list. We do have pre-programmed stage lists, but in the case of just running 6 samples, we can So we have a spot here for the this is in 10x, and we're going to take a position here for this would be position 1. This will be 2. Now you can see actually here the fibers from the collagen, which is a good sign. This is position 3, or flow cell 3. We'll center that here. Okay. This is 4. You see increasing concentrations of the fibers. Call it position 4. Go down. Just a little tighter. We see more fibers here, which is a good sign. 5. And at 100 micrograms per milliliter, you see quite a few fibers here. It's position 6. Now, under saving, we're going to select a directory. The C drive. I already made a file here for live demo. Okay. And then under the multi-dimensional acquisition, we're going to pick a time lapse, and we're going to go for 12 minutes every 30 seconds. 12 minutes. Go from the bottom to the top. And of course, it says the minimum interval is 3.12 seconds. If we go 20 seconds, we'll get a few more frames on this and have a slightly nicer movement. it's important we get started. I'm going to initiate the perfusion at 10 dynes to start out with, and then we'll increase this to 40 when we start acquiring. And the reason we're going to do this pre-perfusion is to focus on the platelets that are being aggregated on the bottom of the plate. So we're going to start this. We see platelets that are forming. Very quickly we go to the FITSI channel, and we go from position 1, position 2, 3, 3 has needs to be a better focus. I'm taking a variety bed. 4, is now in focus for the platelets that are on the bottom. 5 and 6 is in focus. Now, we will begin acquisition and immediately switch this over to 40 dynes. So it's now acquiring in both the bright field and in the fluorescent channel an increasing concentration of collagen. And during this acquisition, John is going to discuss in a little bit more detail the applications of the bioflux and upcoming developments.
Thanks, Brian. I hope everybody can hear me. I'll take you through a very brief presentation here that talks about the company broadly and the bioflux in particular. So we're based in San Francisco. We have worldwide sales and distribution. By now, we've placed in excess of 300 systems worldwide, and we have multiple products in development. The current portfolio consists of the 3 instruments that you see listed here: the bioflux, which is the subject of today's discussion, the ion flux, which is an automated patch clamp system, and the most recent addition to the portfolio is an instrument called the isoflux, and this is a system designed to isolate rare cells in circulation with a particular emphasis on circulating tumor cells. The 3 systems share one very simple design element, and that is they're all microfluidic devices in which one well or one compartment communicates to an adjacent one by means of a channel built below the superstructure of each of these plates. The bioflux, as you know, is one in which most data is acquired by microscopy, as we're doing today. The ion flux is designed to be able to acquire electrophysiology data, and the isoflux doesn't do any analysis on its own. It simply delivers a highly concentrated, purified pellet of cells of interest in an easy to remove and reposition cap. So what does the bioflux do? It simplifies the microscopic study of live cell behavior under flow by making it possible to rapidly add and remove compound to an assay. It provides a platform where one can easily multiplex assays in the same plate, and it makes it possible to manipulate the microenvironment in which these events are occurring. So you can change gas composition above a monolayer. You can make physical gradients across a channel. or even temporal gradients by changing over time certain conditions in the asset. In addition to all of that, it imparts physiological range, shear, force. And this is important, as I'm sure you know, in the study of endothelial cell interactions, and as we're seeing today in analyzing thrombus formation. It's also important in microbiology applications related to the study of biofilm growth or mitigating against biofilm growth. And it makes it possible to study the interaction of a host cell and a pathogen. So how does it do it? The platform consists of 4 components. The controller, which is the pump, if you will, displayed here in the picture at the extreme left-hand side of the screen. A selection of what we call interfaces. This is a way of delivering the gas that is being compressed by the bioflux pump to the top of a bioflux plate. A selection of single-use microfluidic flow cell arrays, which we call bioflux plates. And today we're using a high shear plate. And then a suite of software applications that control not only the instrument, and in today's case, you're seeing a Bioflux 1000Z in action, but also makes it possible to make sense of the image data that is acquired by reducing it to some numerical set of data. We call it montage, and as Brian alluded to, this is our customized version of Metamorph, which is a widely distributed instrument control and image analysis software application. So how does the content of one well travel to an adjacent well through a microfluidic channel? You're seeing a movie, hopefully it's playing on your end, of how that occurs. It's a simple design principle. You fill a well, you make an airtight connection between the plate and the pressure interface, and then under pressure the contents of the inlet move to the outlet across that microchannel, or in the opposite direction, as Brian has showed you at the beginning of this experiment. The pump is unobtrusive. It's a small footprint instrument, probably about the size of a toaster oven, if you will. It's a very precise instrument and provides very rapid and responsive control of the microfluidics in the plate and the contents of those microfluidics. And it has a very broad dynamic range, spanning, as I said earlier, the entire range of conditions one finds in vivo, or almost all of it. At 200 dyne per centimeter squared, you're essentially replicating what occurs in a large blood vessel under conditions of stenosis. So the plate interfaces are what are shown here. They're available in 2 types, one for the Bioflux 200 or the EZ, pictured here in the left-hand side of the screen. And these interfaces couple to the plate by means of these fasteners. There are 4 of them displayed there that are tightened against the receiving couplers in the plate by means of a torque screwdriver, or a Bioflux 1000 interface, which is being shown here on the right, and that couples to the stage, making a sandwich of the plate interface and the stage and the plate that is being used. It's much more ergonomic and makes it very easy to disassemble and reassemble, so that if one needs to add a compound to a reaction while the plate is being imaged, it's a lot easier to do that. Our Bioflux plates start off in life being conventional microwell plates, which are then modified so that a hole is made at the bottom of each well. The microfluidic channel here, illustrated in red, is embedded inside a layer of PDMS. This is a silicone polymer. and then the entire thing is closed off by a large but otherwise conventional thickness cover slip type glass that is almost as big as the entire plate itself. And I just noticed an error here. It's not 180 micron, it's 170 micron in thickness. For both the Bioflux 200 and the Bioflux EZ, and then the Bioflux 1000, plates exist in three types. Bioflux 48 well plate low shear. This has a range of 0 to 20 dyne per centimeter squared. And it's important to point out here that 48 well plates have 24 assays on them, right? Because there is one inlet and one outlet for each assay. So you have 24 experimental channels. And the viewing window is positioned in such a manner that it resides amongst a group or between the 4 wells in each group. There's also a 48 well high shear plate, which is the one that we're using today. The plate geometry is identical to the low shear plate, and again, 48 wells means 24 assays. And then finally, there is a 24 well version in which there are 2 inlets and 1 outlet for each experiment. So if one does the arithmetic, it turns out that a 24 well plate has 8 experimental channels, 2 inputs per channel. And this is used in a variety of other applications that take advantage of the fact that there are 2 parallel laminar flow streams in each of the assay channels. And so applications that use the Bioflux 24 well plate are things like wound healing or chemotactic migration or invasion. It also makes it possible, because there are 2 inlets, to conduct pulse chase experiments. You could add to a single monolayer of cells that occupies the entire width of the channel 2 compounds, either sequentially or in combination with one another. Because we're imaging from the bottom across a very thin piece of glass, Bioflux plates can be used in a variety of imaging techniques, using transmitted light and phase contrast, to epifluorescence, as we're doing today, to confocal microscopy. As you'll probably hear, in fact, as I know you will hear shortly, we will be announcing that we've developed a series of applications in the family of imaging devices that are collectively known as high-content imaging systems. See evidence of that here in the lower right-hand side of the screen, where that image was obtained on a PerkinElmer Operetta, one of such devices. So broadly speaking, the use of our platform is for shear flow dependent assays, as we're doing today in platelet aggregation, or other experiments in which the additional component of shear force is an important part of the experiment, or as a substitute for a liquid handling device and adding compounds at just the right time during a live experiment. Shear stress, I'm sure you know, is a critical parameter. I mentioned this earlier, that our platform spans the entire range of shear forces that one encounters in the vasculature. Here's a cartoon of the common carotid, and if you can see the color coding on that vessel, most of it is green, and that corresponds to about 20 dyne per centimeter squared. But you do get areas, as you see here in the red, where those forces approach 60 or 70 dyne per centimeter squared. And our plates go well beyond that. The evidence in the literature is broad that shear flow is important. Even on gross observation, you see here 2 photomicrographs of our microfluidic channel. On the left, this population of HUVEC cells has been cultured under no flow, and on the right you see population of UVEC cells that has been cultured for 16 hours at 2 dyne per centimeter squared. And so even on gross observation, one can easily discern that there is a cytoskeletal rearrangement in the panel on the right that isn't present in the panel on the left. You will see at the conclusion of this broadcast that we can generate thrombi in our channels, such as you see in these two pictures. In the top, you have kind of a loose aggregate of clumps of platelets, whereas at the bottom here you see well-formed thrombi in the same channel. The importance of physiological range shear flow has also been noted in the literature for endothelial cells, and here's the same example I showed before from the Perkin-Elmer operetta. This is work that was done at the Wellcome Trust in the UK using one of our bioflux instruments, and then the plate was imaged on the Perkin-Elmer operetta. And we have found in the last several years, we've been fortunate enough to place instruments in all the areas that you see highlighted here. Most of, and actually, of all the instruments that we have deployed to the field, they fall into 3 categories of roughly the same size. So about 30% of our instruments are in inflammation, vascular, cancer biology. The other third are in microbiology, and then the remaining third are in kind of a general cell-based assay where people are doing everything from calcium flux experiments to differentiating stem cells under flow to wound healing and other applications. I mentioned earlier that the bioflux plate, particularly the 24-well plate, can be used to deliver compound to an assay. There is a movie here on the left-hand side, and I hope you can see it, where we're pulsing 2 separate compounds. One is opaque and the other one isn't, from each of the 2 inlet wells in a 24-well plate by staggering the pulse. So inlet 1 goes and then stops, and then inlet 2 goes and then stops. And this is illustrated graphically in the panel on the right here through a density measurement. The bioflux family of products is composed of the items you see listed on the left. There is a bioflux EZ, which is our entry-level instrument. This is limited to just using the 48-well plate. The bioflux 200, which can be used in combination with any inverted microscope. The bioflux 1000Z, which is the instrument that we're using in our lab today. This, for lack of a better description, is a bioflux 200 plus a top-of-the-line inverted microscope from Zeiss, and includes the software that makes it all run seamlessly together. The bioflux Quattro is an add-on to either the 200 or the 1000Z, and this device makes it possible to run 4 additional plates outside of a microscope stage, so that one can subject some monolayer of cells to up to 96 additional separate treatments. And the bioflux prep station, which is a device that can be stored in a hood, purely for filling plates without the need of having to move the bioflux itself from the cell culture room to the microscopy suite. So the bioflux EZ looks like this. As you might expect, the pump is essentially, at least from its outward appearance, identical to the bioflux 200. and it uses a pressure interface that requires clamping by hand to a plate. The BioFlux 200 looks very similar. And then the BioFlux 1000, which makes it possible to minimize user intervention and run kinetic experiments by using BioFlux technology essentially unattended. And the BioFlux 1000, again, is comprised of a microscope, the pump itself, the suite of software applications that automate the entire device. Here's an image of a Quattro. What is not shown here is the pressure lines that connect the BioFlux pump itself to the pressure interfaces, but you can easily envision that. And finally, a summary of what we feel are the important advantages of using BioFlux in the context of the applications I've enumerated. Our entire system is designed for sterility, so nothing in the hardware ever comes in contact with any biological component. Just keep in mind that the way we get things to occur in a BioFlux plate is by driving the contents of a well under pressure across a channel to an outlet. So unless somebody trips on the way to the microscope, nothing in the plate ever comes in contact with the interface or the instrument itself. It has broad dynamic range all the way from 0.1, and I'm sorry, that is a typo, 0.1 to 200 dyne per centimeter squared. Experiments can be run from room temperature to 40 degrees C, and all of our instruments, except for the BioFlux EZ, come with a plate heater. The device has a very fast response time on the order of half a second. It is possible to run experiments in pulsatile flow with the purchase of an additional software module to our system. The flow is bidirectional. It can go from inlet to outlet and vice versa. It's a highly reproducible system. We use stringent manufacturing controls in our plates. And if you run an experiment on one type of plate today and then intend to run a repeat of that experiment next week on a different plate from the same product category, the results would be the same. Our system makes it possible to run up to 96 experiments in parallel, so it's higher throughput than anything else on the market. And that reduces the variability that one encounters when having to sequentially run experiments over time. And our plates are conform to what is known as the SBS standard. So it's a standard footprint plate in the various configurations that you've seen. So at this point, I'm going to turn it over to Brian again. Thank you for your attention.
The experiment is still going on, but we can go ahead and stop it at this point. Most of the events that were going to happen already happened while John was discussing the BioFlux system. After acquiring a data set, one of the convenient ways of looking at it is going through with Montage under the Review Multidimensional Data. I'm going to select the directory to pull it off, which was the live demo platelet. And we had one acquisition set. We hit View. And here we had 33 acquisition points. If we had let the experiment run longer, it would have gone to 37. And we have 6 different stage positions corresponding to the different conditions on the different ECM proteins. So if we go here and use the right mouse button, we can select all of these and look at FITSI, which is interesting there. We're going to look at position 6, which was 100 micrograms per milliliter, and hit load images. What we see here is that we start out with just a little bit of accumulation, and very quickly, within a few minutes, we have reached a saturation point of coagulation. Now, what's happened after this is that the thrombus has moved on the flow cell, and you don't see anything else after that. And the reason why is that the blood has stopped. It has glued itself here. But the actual glowing thrombus from the viewing region has just moved slightly to the right, and so fortunately you don't see it anymore, but you do see it going to the point of saturation. So this is, at this point, time 10 of 33, the highest point on the thrombus. So to analyze this, we're going to use a threshold for light objects. In fluorescence, you want to use for light objects. In bright field, for example, if you're using that for biofilm, you'd want to do it for dark objects. And so we do an auto threshold for the light objects here, and we're going to look to see if it corresponds, which it does. And then we're going to take a rectangular region of the channel here, and we'll go to MM standard, measure, and then to region measurements. Excuse me. Still getting over the crud from the last trip I took. This window has ballooned out, but we're going to take it back into control here. There we go. And so what we plotted here is the thresholded area versus the image plane, and we can change that to elapsed time. So we have a quantitative measurement besides the plane, milliseconds. And from here we can, if we'd like to, we can export this data by opening a log to a dynamic data exchange file, which we'll put it in Excel. Press OK. Okay. We have Excel here. We have Excel. Let's try this again. Well, as Murphy's Law would show, something would glitch on the computer. This is a multiple-use computer. So anyhow, we can see the kinetics behind this rise in coagulation. And so let's compare that to another file. And I was noticing that number 4 had a very nice coagulation cascade here. So I'm going to expand this out a little bit so we can see it. This is channel 4. We're going to auto threshold for light objects. And actually, when we go to, first we'll go to threshold image here. I'm going to check what the settings were. 1412 to 4095. And we're going to do that to correspond with this one. Okay. That way we're looking at apples to apples here. We're going to rectangular region of the section here. And then we will go to region measurements. Actually, what we can see here is that there was a thrombus formation, and then it fell away, and then we had a very gradual, which was actually what we were expecting. So we would look at this curve right here and consider this to be a, let's see. we would look at this area right here. If we look at the video, we would see, or the stack, that it does come to a saturation point. Wait, no, I'm sorry. This is area 2. Yeah. There's a saturation point here, so we could look at just the acceleration to this point too. And we will look at a comparison of the BSA, which is the negative control. In the case of the BSA, we really didn't have any coagulation at all. So one more thing we'll do for this the video that we had seen is we're going to we will put this into an AVI format using ImageJ. So we want to save this. This is will be a TIFF video, and we're going to save it as 100 grams of collagen. And then we're going to go to ImageJ. And we'll also use the file format here to observe that in the video that we have, that stack, it currently reads as 93 megabytes. I'm going to open the video, the stack. This shows the coagulation as it occurs over time. And we'd like to save this as an AVI in a compressed format to JPEG. And we would do maybe 2 frames per second, which would make approximately 15-second video. It's okay. Save. And now we have a video that is 1.5 megabytes instead of 93 megabytes. We'll load it up in. So this is something you can put on your PowerPoint slides when you're giving presentations. Well, with that, I want to thank you all for attending, and please feel free to email myself, brian.haynes@flexionbio.com, or info@flexionbio.com.